Welcome once again to session 5 of UGBS 301. My name is Charles Jemfi Ofori. In this session, we'll be discussing probability and probability distributions. Life is full of uncertainties. There are a number of things that we go into that we are not sure of. For example, how do you plan this year's meeting next year's electricity demand, knowing that demand for next year is uncertain? How do you plan, let's say, your activity for tomorrow, knowing that you don't even know whether it would rain tomorrow or it wouldn't rain tomorrow? So we are going to discuss how you model real-world problems that involve uncertainties using probability distributions. In our previous courses, we did an introduction to probability. We talked about expectation, we talked about variances, we talked about coefficients of variation. This time we also want to look at probability distributions. So our main concern here is to look at the concept of random variables, discrete and continuous probability distributions. And under discrete probability distributions, we want to look at the binomial distribution, the Poisson distribution, as well as the hypergeometric distribution. Then under the continuous distribution, we would look at the normal distribution, which will be discussed in the next session. But for this session too, we would also be concerned with finding the mean and various calculations of these random variables. So a random variable is just a real valued function which is defined on the sample space. And these values or these variables assign values to each of an experimental's outcomes. For example, if you have 3 tosses of a coin and we are interested in the number of heads that will be obtained, and x is the number of heads, then you will say that x is a random variable that can assume the value of 0, 1, 2, or 3. Because if you turn a coin 3 times, you can get the head coming 3 times, you can get the head appearing once, you can get a head appearing twice, or you can even get no head appearing at all. So there are other examples of random variables. Another example is, what grade do you anticipate to earn in UGBS 301? Yes, I expect that most of you would expect to earn an A. But the possible outcomes is ranging from A to F. Of course, if you say A is 1, B plus is 2, B is 3, represent C plus as 4, represent C as 5, D plus as 6, and F as 7, then your grade can be a random variable X, which represents your possible grades, which is given from 1 to 7. This is an example of a random variable. Now, a random variable can also either be discrete or continuous. A discrete random variable has only a finite number of possible values. Also, a discrete random variable also contains packs of whole numbers. A continuous random variable, on the other hand, has a continuum of possible values. So as you can see, for a discrete, you have a finite value that are packs of whole numbers, but the continuous one just runs continually on the continuous scale. Let's look at some examples of discrete random variables. The number of times a 4 comes up when a die is rolled twice. Then the random in this case is that if a die is rolled twice, there's a possibility that a 4 will not appear, or a 4 would appear only once, or a 4 would appear twice. In this case, the values that are represented in here is that x can be 0, x can be 1, or x can be 2. This is a discrete random variable. Also, the number of heads that are obtained when a coin is tossed 4 times can also be a discrete random variable that will range from 0 to 4. Other examples of discrete random variables are the number of complaints per day, the number of TVs in a household, the number of cars that are passing between 7 a.m. and 9 a.m., and the number of rings before a phone is answered. One way of distinguishing between a discrete random variable and a continuous random variable is that discrete random variables do not have fractions or decimals or anything of that sort, but most of them, they are whole numbers. For example, you can't say that you recorded 2.5 complaints in a day. Neither can you say that there are 5.5 cars that pass between the hours of 9 a.m. and 7 a.m. and 9 a.m. But of course, we can see that there were 1,000 complaints per day. There are about 200 TVs in a household. There are about 500 cars passing between 7 a.m. and 9 a.m. And then of course, we can also have other discrete random variables that have only two possible outcomes: gender, either a male or a female, nothing in between; whether a machine is defective or not; or in a game, whether you win or lose. For a continuous random variable, it can assume any value on a continuous scale or on a continuum. For example, the thickness of an item. Now, another easier way of seeing a continuous random variable is that they can be represented by any number at all on a continuous scale, be it rational numbers, be it irrational numbers, be it decimals, be it fractions, you name it. So, the thickness of an item, for instance, is a continuous random variable because we can have the thickness to be 2.5, maybe inches, or 3.0, 4.8, and so on and so forth. The time required to complete a task, 1 hour, 30 minutes, can be translated to, let's say, 1.5 hours. The temperature of a solution measured in degrees Celsius, you can have temperatures ranging from 26.5 degrees and so on and so forth. The height of an individual or anything is also a continuous random variable. Now, this can potentially take on any value depending only on the ability to measure accurately. Of course, when we did probability in our earlier course, we found the mean of a random variable, that is the expectation, we said is the value of x multiplied by its probability. And we're also going to use the mean very well in this session when it comes to the probability distributions, as well as the variance of a random variable. So, we have some types of random variables. We mentioned that there are certain discrete random variables that we would want to look at and certain continuous random variables that we want to look at. And for the discrete random variables, we are looking at the binomial distribution, the Poisson distribution, and the hypergeometric distribution. Therefore, we start with the binomial distribution. Now, in a binomial distribution, we are using this distribution to describe real-world phenomena. And in this distribution, we have that events occurs only in two possible outcomes. And this event is repeated multiple times. So it describes the distribution of a success in a series of trials. That is, in out of about n trials, what's the probability that x of them succeed? What is so striking about the binomial distribution is that we have only two outcomes: a failure and a success. For example, a manufacturing plant can either label their items as either defective or acceptable, or let's say non-defective. A bidding firm or a firm bidding for a contract will either get the contract or they will not get the contract. A marketing research firm will receive a survey response of, say, yes, I would buy, or no, I would not. Nothing in between. And then new job applicants will either accept the offer or reject it. Now, in all of these examples, you see that we have each of the examples having two basic outcomes: either a yes or a no, either defective or non-defective, either they get the contract or they don't get the contract, or either they accept the offer for employment or they reject it. Let's look at certain characteristics of the binomial distribution. The trial or the binomial event has only two possible outcomes. That's what you said, either success or failure. And then there's a fixed number of identical trials. The trials of the experiment are independent of each other, and then the probability of success remains constant from trial to trial. And if the probability of success is P, then the probability of failure, which is also denoted as Q, is 1 minus P. So if success is P, failure is 1 minus P. Now, in combinations or in binomial distribution, we'll be using combinations a lot. Actually, in our discrete random variable calculations, we'll be making use of combinations a lot, especially in binomial distribution and in the hypergeometric distribution. Now, a combination is just the number of ways of picking x unordered outcomes from n possibilities. For example, how many times can you say select about 3 people to form a committee out of, say, 5 people? How many times can you choose 5 marbles out of, say, 10, a collection of 10 marbles? These are all part of the combination, what we call combinatorial analysis. And a combination of, say, n combination x, which is written as this ncx, is mathematically expressed as n factorial all over x factorial times n minus x factorial. I know in the beginning this may look quite outrageous to you, but with practice and solving a lot of questions, you will be able to understand and adjust to this formula. This combination can also be found on your calculators. Factorial notations can also be found on your calculators. Now, n factorial is just n times n minus 1. That is the product of n as it reduces by a value of 1. 0 factorial by definition is also 1. And n combination x is also called the binomial coefficient. In fact, you will see this n combination x arising most of the time in our binomial random variable. Good. So our binomial distribution formula is given as this. You have n combination x, which is actually represented as the n factorial over x factorial, then the n minus x factorial, times p raised to the power x times q raised to the power n minus x. Don't be scared with this formula. We are going to break them down and identify what each of these parameters are. So, the p of x is the probability of x successes in n trials, with probability of success p on each trial. X here is the number of successes in the sample, and x can run from 0 up to n. P is the probability of success per trial. Q is the probability of failure given as 1 minus p, and n is the total number of trials. For example, let's say that in an exam, the two outcomes are you either pass or fail. And you write, let's say, the exam about 4 times. And you want to look at the probability that you passed 3 times out of the 4. And your probability of success is, let's say, based on your academic performance, you have a 60% chance of passing. Then it means that your n is the number of times you've written the exam, which is 4. Your x is the required probability. Let's say that you are looking for the chances that you pass in 3 out of the 4. So your x is 3. And then your p is the probability of success. the probability that you pass the exams, and we said there's a 60% chance, therefore your P is 0.6. Now, if there's a 60% chance of you passing, then likewise there's a 40% chance of you failing. And therefore, your Q will be 1 minus P, which is 1 minus 0.6, which gives us 0.4. Let's take an example for the binomial distribution. At UGBS, 30% of the students are majoring in finance. In a sample of 10 UGBS students, what is the probability that exactly 3 of them are majoring in finance? How would you know that this question is actually a binomial distribution? First of all, you are interested in asking yourself, are there 2 outcomes in this question? For example, the outcomes here are students who major in finance and students who do not major in finance. So, this is a binomial random variable, and the sample size is 10, that is n is 10. The probability of success is 30%, that is 0.3. And we are looking for the probability that exactly 3 are majoring in finance. Therefore, we are looking for the probability that x is equal to 3. Before you attempt to solve any question on probability distributions, always, first of all, identify your random variable of interest. So for this particular question, we will say that we should let x represent the number of students who are majoring in finance. The number of students who are majoring in finance. Therefore, if you are expecting or you are looking for the probability that exactly 3 people are majoring in finance, then it means that you are looking for the probability that x is equal to 3. When you go back to our binomial distribution formula, we are saying that the whole of this can be represented by n combination x. N combination x, which is the whole of that. So if you go back to our solution, we are saying that since n is 10 and then x is 3, we have 10 combination 3 multiplying the probability of success. Remember that it is p raised to the power x. So our p is 0.3, our x is 3, and then 1 minus p, that's the probability of failure, which is 0.7, times n minus x, that is 10 minus 3, which is 7. Therefore, our probability of exactly 3 students majoring in finance is giving us 10 combination 3 times 0.3 raised to the power 3 times 0.7 raised to the power 7. 10 combination 3 gives us 120. 0.3 raised to the power 3 times 0.7 raised to the power 7 also gives us 0.0022. You multiply, you get 0.2668. In other words, there's approximately 30% chance of finding exactly 3 students majoring in finance. Note that we are dealing with probabilities, and probability would always lie between 0 and 1. That means that you need to check your work. If you find that you calculated the probability and you had a negative value, or you had a value which is more than 1. In the second part of the question, we are being asked that in a sample of 10 students, what is the probability that at least 3 students are majoring in finance? At least 3 students are majoring in finance. We learned from linear programming that if we say at least 3, then we are looking at something which is more 3 or more. At least 3 can be rewritten as probability that x is greater than or equal to 3. Probability that x is greater than or equal to 3. Now, given that it is probability that x is greater than or equal to 3, then it means that x can be 3, x can be 4, x can be 5, it can be 6, it can be 7, it can be 8, it can be 9, and it can be 10. This will mean that we need to put each of these values of x into the binomial distribution formula before we can solve. That's about 7 or 8 values of x. Putting each of these will be a very cumbersome process and it's going to waste our time. Therefore, what we did was to work from the other way around. If x is greater than or equal to 3 is what we are looking for, then we can say that let's find the probability that x is less than or equal to 2 and then subtract the entire value we get from 1. So you see that probability that x is greater than 3 can be rewritten as 1 minus probability that x is greater than or equal to, x is less than or equal to 2. So instead of putting in values that will range from 3 up to 10, I'm just going to put in values that will range from 0 to 2. So we have 1 minus probability that x is 0 minus probability that x is equal to 1 minus probability that x is equal to 2. Actually, you could have also done it 1 minus, you introduce a bracket, probability that x is equal to 0 plus probability that x is equal to 1 plus probability that x is equal to 2. That means that we are summing the probabilities in here, then we subtract the resulting one from 1. This one makes life simpler and it makes your solutions much simpler and easier to do. So we have the probability that x is greater than or equal to 3, giving us 1 minus the first one when x is 0, p raised to the power 0, p raised to the power x. First of all, we also have 10 combination 0, 0.7 raised to the power 10, that is for x to be 0. Then for x to be 1, we have 10 combination 1, 0.3, which is p raised to the power 1, times 1 minus p raised to the power n minus x, in this case, which is 9. We have likewise a similar one for x being equal to 2. And when you solve, you have 0.617. So it means that there is about a 61.7 chance of getting at least 3 students majoring finance in a sample of 10 students. As we said, we'll be dealing much also with the mean and then the variance of the binomial distribution. And in the binomial distribution, the expectation or the mean is just n times p. In other words, the expectation is just giving us the number of trials multiplied by the probability of success. Similarly, our variance is giving us the number of trials times the probability of success times the probability of failure. So we have our n being equal to the sample size, our p being equal to the probability of success, and our q being equal to the probability of failure. And our standard deviation is also giving us sigma equals to the square root of our variance, which in this case is the square root of npq. You could also use binomial tables to solve a binomial question. For example, if n is equal to 10, p is 0.35, and our x is 3, then our probability that x is equal to 3, you look for the table that has n to be 10, the corresponding value of x, which is 3, then the corresponding value of p, which is 0.35, and then our probability is the point of intersection here, which is 0.2522. You can also play along with these other values and you would find their respective probabilities using the binomial tables. We now move on to the next distribution, which is the Poisson distribution. The Poisson distribution. Unlike the binomial distribution, or in most cases, binomial distribution are good or are useful when n is finite, that is, when you know the sample size. But there are cases where the possible outcomes cannot be determined, and therefore the binomial distributions cannot be applied where n is infinite. For example, although you can count the number of potholes per mile, we cannot count the number of non-potholes per mile. In such situations, we will need another probability distribution to describe such natural phenomena. The Poisson distribution actually looks at the possible outcomes of an event within a certain interval. The interval could be time, or the interval could be space. For example, we could be interested in the number of arrivals at a certain checkout counter within an hour, the number of arrivals of maybe patients at an OPD in a hospital, the number of arrivals in maybe a barbering shop within a day, within an hour, or within 30 minutes. Or we can also look at the number of errors that are made per page by a typist. All these are number of occurrences within a certain interval. And then the interval that we're given were time or space. So this is how the Poisson distribution formula actually looks like. As you can see, the probability of success is given as lambda t raised to the power x. We have e, that's an exponential, lambda t all over x factorial. Now this lambda t is actually the number of occurrences within a time interval t. And in some situations, lambda t can be expressed as mu. So if you express all lambda t's as this mu, you are going to have mu raised to the power x e to the negative mu all over x factorial. So we have t being the time segment of interest, say 2 hours, 1 hour, 45 minutes, and so on. X is the number of successes in the segment of interest. So for example, if I'm looking for the number of customers that arrive at a certain checkout counter in, let's say, an hour or in 2 hours, our X will be the value that I want. Let's say I want the probability of 5 customers arriving within the hour. Lambda is the expected number of successes within the time interval, and then mu is the mean number of occurrences in an interval. In fact, the lambda and the mu always go hand in hand. Then E is the base of a natural log, which can be found on your calculator, but the actual figure is 2.71828 and so on. And lambda t is given as mu. As you can see, lambda t has been represented as mu here. So if mu is 20 per every 2 hours, then you have that t is equal to 2 and lambda is 10 per hour. Let's take an example for the Poisson distribution. A study conducted at Whole Foods Grocery shows that the average number of arrivals at the checkout section of the store per hour is 16. Further, the distribution for the number of arrivals is considered to be Poisson distribution or Poisson distributed. What's the probability of 12 number of customers arriving at the checkout in 1 hour? How do you differentiate this from a binomial distribution problem? You realize that in here there's nothing like probability of success, there's nothing like number of trials. All that we have here is the number of occurrences within the time interval. And therefore, as we did for the binomial distribution, we will say that let X represent the number of customers that will arrive at the checkout counter within the time period allotted. That means that we are looking for the probability that X is equal to 12 because the question demands that we look for this probability. And our mean, or our lambda t, is 16. 16 customers arriving in 1 hour. That means that our lambda t is 16. So we just fix everything into the equation. Mu x, that is 16 raised to the power 12, e negative 16, that is e raised to the power negative 16, all over 12 factorial. And that's going to give us 0.0661. In other words, there's about a 6.6% chance that we are going to have exactly 12 customers arriving in an hour, given that the average number of arrivals is 16 per hour. Very simple, isn't it? Let's look at another example. Patients arrive at the emergency room of Mercy Hospital at an average of 6 per hour on weekend evenings. What is the probability of 4 arrivals in 30 minutes on a weekend evening? Now, there's a sudden twist to this question. As you can see, in the previous question, the preamble said the arrivals per hour is 16, and the question demanded that we find 12 number of customers arriving per hour. In other words, the interval that was given in the preamble was the same interval that was given in the question. But in this question, we see that the interval that is given in preamble is on a per hour basis. But the question is asking for a probability of 4 arrivals in 30 minutes. So you ask yourself, on the average, if 6 people can arrive per hour, then how many people do you think on the average will arrive in 30 minutes? Your guess is as good as mine. If 6 people will come in an hour, then we expect that 3 people would arrive in 30 minutes. Therefore, our mu, or our lambda t, wouldn't be 6, but it would be 3 per 30 minutes, because this time we are looking for a time interval of 30 minutes. Aside that, nothing changes. We put everything we have into the formula, that we have the value of lambda raised to the power x, we have the value, the e raised to the power lambda, or mu, all over 4 factorial, and you get 0.1680. That tells us that we have about 16.8% chance of having 4 arrivals in 30 minutes on a weekend evening. So please, anytime you are given a Poisson distribution to answer, you need to check how the intervals are given you. Ask yourself whether the interval given you in the question is the same interval that is given in the preamble. If it's the same, you can go on and use the formula. If it's not the same, then you need to change the value to reflect whatever is given in the question. Also, the Poisson distribution has the mean and then the variance. The mean of a Poisson distribution and the variance of the Poisson distribution are the same, which is lambda t for mean and then for variance respectively. And of course, the standard deviation will be given as the square root of lambda t. Just as we used tables for the binomial distributions, we can also use tables for the Poisson distributions. For Poisson distribution, all we need is the value of x as well as the value of mu. So if you remember, our x was 4 and then our mu was 3, and we have a probability of 0.160. So there's a short exercise for you. Find the probability that x is equal to 2 if lambda equals 0.05 and t is equal to 100. Now, if lambda is 0.05 and then t is equal to 100, then it means that lambda t is equal to 100 times 0.05. 100 times 0.05. And we are looking for the value of x equal to 2. Put them together. You can either use the formula or you can use the tables to answer that. We move on to the next probability distribution, which is called the hypergeometric distribution. The hypergeometric also is looking at n trials taken from a finite population or sample of size n. And most of these samples are taken without replacement. So mostly we are concerned with finding the probability of small x successes in a sample where there are big X successes in the population. Basically, the hypergeometric distribution is showing you the probability that you can find, assuming that you have a population, and within the population there is a group within the population that have a certain particular attribute that you are interested in. For example, let's take it that we have a class of size 50. Out of the class of the size 50, we have about 10 people being left-handed students. So it means that our big N is our population size, which is the total 50. And then our big X is the number of students who has the required attributes, the attribute of interest. In this example, let's say the number of left-handed students. So our big X is 10. Now, assuming I take a sample of size, say 5 at random from the population, that means that small n is 5. My interest is that what is the probability of finding, let's say, 3 students who are left-handed out of the sample of size 5. So we have a population of size n, big N equals to 50. Within the population, there is a size of big X equals to 10, that is the number of students being left-handed. I take a sample of small n, let's say 5, and I'm interested in finding the probability that there are 3 left-handed students in this sample of 5 that I've taken. That is what situation that warrants a hypergeometric distribution. The relation or the probability distribution for a hypergeometric is given as big N minus big X combination small n minus small x multiplying big X combination small x over big N combination small n, where n is the population size, big X is the number of successes in the population, or the number within the population that has the required attributes. Small n is the sample size, and then small x is the number of successes within the sample. That is the number of people, of individuals with the required attributes within the sample that you have. And mind you, small n minus small x represents the number of failures in the sample. Let's take an example, and I know you'd understand this perfectly. 3 light bulbs were selected from 10. Out of the 10, 4 of them were defective. What is the probability that 2 out of the 3 selected are defective? So we have a population of size 10, and out of the population of size 10, there are 4 defective bulbs. I pick a sample of size 3 light bulbs from the 10, and I'm interested in finding the chances that I'll get 2 defective bulbs out of the 3 selected ones. Therefore, our big N, which is the population size, is 10. Our big X, the number of bulbs with the required attributes in here is the defective bulbs within the population is 4. My sample size, small n, is 3. And then the number required, or the population, the probability of 2 defective bulbs out of the sample, that is small x, is being equal to 2. So our probability that x is equal to 2 is given as big N minus small s combination small n minus small x, which is 10 minus 4, that gives us 6. Combination small n is 3, small n x is 2, so 3 minus 2, which is 1. Big X combination small x, that is 4 minus 2, 4 combination 2, sorry, divided by big N combination small n, which is giving us 10 combination 2. When you do all of these, 6 combination 1 is 6, 4 combination 2 is 6, 10 combination 3 is 120. That gives us 0.3. In other words, there's a 30% chance that 2 of the 3 selected bulbs are defective. So far, we've learned the discrete random variables, the hypergeometric distribution, the binomial distribution, as well as the Poisson distribution. We said binomial distribution is for situations where there are 2 outcomes, a trial that involves 2 outcomes, and then we have n identical trials. For the Poisson distribution, we are looking at the number of occurrences within a time interval, and for the hypergeometric distribution, we are looking at the number of items that has a certain attribute within a sample selected from a population of size big N. That ends session 4. Thank you very much.